Hello all, welcome to this interesting video session on conic equations. Today we are going to derive one of the most important conic equations which you might have seen in different textbook. So today we'll try to derive this equation in a very simple way. The basic application of this equation is you can predict what type of conic profile, whether a planet, whether any celestial body is been exhibiting. Okay, when a spacecraft is placed in certain orbit and or placed in a certain energy orbit, rather we could say. So, what is the profile that it is going to exhibit, and what is the planetary uh, path which is been exhibited when it is separated by a different radius, or when it is separated by a different planets of different masses. Okay, so in these conditions we try to understand what is a basic profile or basic orbit, or what type of orbit that the celestial body is exhibiting. So this equation plays a very important role in determining what type of path a celestial body is exhibiting. Okay, this is also in accordance with the Kepler's law. So Kepler's law, as we know, it is applicable to ellipse, and now the equations may change with respect to the conic profiles. Okay, so basically, in order to understand conic equation, we should firstly see what are conic profiles, or what are conic curves, which is been derived from our cone. Okay, so we won't go into deeper aspect of it, but we'll try to highlight some of the important stuff, because already these things we have already covered in your elementary schools and lower classes, so we don't go much into the deep, but we'll try to understand how this is going to give you some insight. So let's say we have a cone or something which is being shown here. So this is going a right circular cone. It is having a base of exactly a circle. So while drawing, you can use your instruments and you can make this as a circle. So you try this is as a circle. Okay, can be a perfect circle. So this is going to be a circle. Now let's say this is going to be the circular profile. Okay. Now let's say I'm going to cut this circle. Okay. Now I am having a baseline. Okay. With respect to the baseline, parallel to the baseline, I'm going to give a cut with a knife or something. So now you take out this cut portion, and if you take this cut portion and if you observe in the bottom view, you can see something just like this, similar to this profile. So this is basically again a circle. So this there is one curve. This is also called as a reference conic profile. This is also called a circle. Okay. So this is called a circle. Now you increase your parallelicity a bit in a slanted position. Now let's say you are going to cut in a slightly slanted manner. Okay. Now you are going to get a profile something just like this. Okay. Now you are going to get something like this, and now you draw a curve like this. Now this is going to be your Now this is going to be your ellipse. Okay. Now this is going to be your ellipse. Now again you increase your slant of cut. So again you are cutting in the slanted direction again. So this time you will be getting more curve over here. So you need to consider the full cut. Okay. So up to this much we have cut it. Okay. So up to this much we have cut. So that means it can go up to a big slant. Let's say this is a big slant. Okay. Now if you draw like this, okay, and again if you draw again a profile like this. Okay, so this is going to be your parabola. Okay, now let's say you're going to cut your conic in this direction. Let's say I'll use a different color so that you'll get to know what is a cut over here. So I'm going to cut in this manner. Okay, I'm going to cut in this manner. So this is which is pretty interesting actually, right? So now if I draw here something like this, okay, Again, I shade here a little bit. So this is going to be your parabola. This is parabola. Now this is going to be your hyperbola. We have a parabola over here. We have hyperbola here. So it's all the conic curves. Okay. Now let's say your eccentricity exhibits for all these curves. Okay. Because circle is a standard curve, so with respect to circle there is some deviation which has been happening with respect to all the profiles. So there comes eccentricity, which is nothing but your e value will be ranging from 0 to 1 for an ellipse. For parabola your e value is going to be 1. Okay, for hyperbola it's simple, your e value is going to be greater than 1. Hope this is clear. And these things you have already learned in your primary classes or a metric classes you have learned. So this you should keep in mind. Your eccentricity is a physical meaning. It is basically I have showed you. It is a deviation from the circle. How much deviation? Maybe from 0 to 1. Okay, so this ratio is going to be 0 to 1. Again, this profile is going to be equal to 1. And e equal to 1 is greater than 1 for a hyperbola. Okay, so all these curves will be exhibited, all the planetary motion. Okay, for any celestial objects or any asteroids, if you consider, all these curves are being applicable. Okay, so being said that, we'll just move on to the next topic. So we need to understand a little bit more clear. Okay, now let's say we have a movable uh, wall or something. Now I take a movable wall. Okay, let's say you can draw it somewhere neatly. Okay, it's okay. Now you have some wheels here. Now let's say you have some wheels. You have some wheels here. Okay. And now I am drawing some kid. It's not me or some other person is drawing some circle here. So we have a circle. Okay, let's say this is going to be a circle. Okay, now let's say the geometric center of the circle is going to be C here. Okay, now what I am doing is like I always take, okay, now I need a laser source. Let's say I have a laser source. Okay, I am just passing some laser source onto this one. So this is a unidirectional source. As you know, laser is a unidirectional source. Okay, so this is having some focus. This is going to be, so focus is being coinciding with the circle geometric center. So focus is the focus of the light source. Okay, now what I am doing, a person, okay, a person who is trying to, okay, trying to push this object. Okay, now this person is trying to push very hard. Okay, this object, okay, is trying to push this object in this direction. Okay, now let's say this is a person and he is trying to push. Okay, he's trying to push this object in this direction. So that means with the wheels it may travel at a some distance, let's say this direction. Okay, but your focus is going to be the same, your geometric center going to be same, but this time your focus will be trying to impinge. Okay, now let's say we have the board here. Okay, now this might have gone somewhere here, so I'll draw here. So this is my board. Okay, this is my board, and this time your focus is going to be, now I'll draw it, it's very simple. Okay, now this is a simple curve again, slightly. So this time your focus is going to be here. Okay, take here. So this time your focus is going to be here, which is a fixed one. So this is the focus value, and now this is the geometric center. Hope it is visible for you. So this is the center. Okay, and now this is impinging on the focus, and now this is the source. Okay, now if I draw this curve, okay, if I draw a curve like this, now let's say I have a curve like this. Okay, now that means there is a focus which is being deviated from the center of this circle. So this circle already you can call this is an imaginary circle. Okay, this is called as an imaginary circle. We are imagining some point having some center, and you are going to have an imaginary circle. So this is going to be an imaginary circle, and this is going to be a focus. So as we have told, now you can draw this point here. Now we can draw some. Now this time I'm drawing this imaginary circle, something like a dotted one. Okay, so this is going to be my C, and I am going to represent this by an F, which is the focus. Okay, now I take some distance. Let's say this is my distance, and I'm going to draw. Before drawing that, I will draw one line here. Okay, so this is called my directrix line. Okay, so this is called the directrix line. Now this is the focus. Now with this distance, I am drawing some profile like this. I don't know what profile I'm drawing, but this is some profile which is going to touch me there onto this side. Okay, so this is going to touch onto the circle, this one. So now we have a focus, okay, and we have a directrix. So this is a basic profile of a conic. Okay, now you neglect the imaginary circle. This is some focus. Now this is called as the conic curve or conic profile you call. So this is basically a conic profile or conic curve having a focus, and there is always a distance from this vertex to this directrix. Okay, that you should be aware. So if I draw a line, okay, let's say I'm drawing different lines here. Now let's say we have a line here. I have a perpendicular line. I have again one more line. Let's say A1, A2, A3. Okay. Now this is a distance from focus to any vertex, perpendicular distance. Okay. Now as we see that your A1 is impinging on some points here on the vertex. Now I am drawing a point from here to here. Okay, it should be straight actually. So this should be straight, which is be hitting onto the directrix. Now we define a property which is called A1. Okay, we define a property, let's say it's also called as a definition. Okay, now from this distance or this distance is going to be B1, B2, and B3. Okay, now we always define something that is A1, that is a distance from the focus to the vertex, and from vertex to the directrix. Okay, so that is going to be E value. Again, A2 by B2 is going to be E. Okay, A3 by B3 is going to be E. That means for this particular curve, okay, your E value is going to be a fixed one. Okay, if this is a parabola, then probably all the E values is going to be equal to 1. If this is a hyperbola, then E value is going to be 2, 3, 4. So that means A1 by B1 is equal to 3. And if it is a circle, then probably you won't exist any A1, A2, A3. This will straight away coincide with the center of the focus, and you will get some imaginary circle which you are going to see in the first case. Okay. So instead we have a deviation from the center, okay, of an imaginary circle, and that is why your eccentricity comes into picture. I hope this is clear for you. Okay, any deviation from circular position or circular path, we define it is by eccentricity, which is actually a definition. That means the distance from the focus to the distance to the direction. Okay, that is called as the eccentricity value. If eccentricity is 0, that means your A1 is going to be 0. That means it is going to hit onto the imaginary center and forms an equidistant point, and which ultimately results into a circle. Okay, I hope this concept is clear. Okay, anywhere if you draw any lines here, A1, A2, A3, and divide by the lines from the point to the directrix, okay, A1 by B1 is going to be your E value. Okay, that is going to be the E value which we have already seen. So this thing you have to keep in mind. So as we told, this is the thing. So now let's come to the main part. Now I want to take this curve a little bit. Okay, so I'll try to create a geometry for a conic profile. Okay, now let's say we have a conic profile as shown in this diagram. Let's say I'll draw a diagram like this. Okay, you can use your ruler to make this everything stuff more straight. Okay, because I prefer most freehand sketch for easy explanation. So that is the reason I'm doing here. So I represent a conic profile. I don't know what is a cone, which is being what is the conic profile that I'm going to exhibit. Let's say I have a conic profile like this. It can be hyperbola, it can be parabola. Okay, it can be a huge ellipse. Okay, let's say now let's say I have different points which I need to explain. Now let's say you have a focus point here. Okay, now let's say you have a focus point. You have a focus here. Okay, so this should be very clear. Now you should be in a position to draw it again. Okay, you have a focus point here. You have a directrix. Okay, and now let's say I'm drawing a curve. Okay, with some radius r or something, which is bit which will be helpful for you to derive a little bit. Now let's say you have r or something which will be helpful for you to visualize. So use a different color or something. So this is going to be your r. Okay, this is going to be your r, and this is going to be your theta value at some theta value. Now we consider a point here which is coinciding with this point p here, and we draw a perpendicular line so that we get an angle of 90 degree here, and we denote that point as to be a or something. Okay, we can denote that point as to be a, so I go with a here. Okay, now I go with a and I have a point, so this is from here it is going to hit this directrix. Okay, let's say this is point b, this point is b. Okay, now from this point you are going to hit this point again. Okay, now that is going to be your again your, you can tell it's b1 or something, or we can use this the same color or something. So we have d1, you can tell d1, let's say d1. Okay, now now it's bit okay now. So now let's say you have a semi lattice rectum which is been drawn from here. So any for any curve, okay, if you told you have a curve like this, you have to keep this also in mind, because this you have studied in your elementary classes. So if you have any section like this or a parabola or something, okay, any conic profile you take, you have a focus. So perpendicular drawn from the focus is going to be something called your L value. So that is called the semi lattice rectum. Okay, so another 50% is going to be in the down, so the total is going to be 2L. Okay, so 2L is actually called the lattice rectum. Okay, 2L is actually called the lattice rectum. So here we'll consider the semi lattice rectum, which is being drawn from here to here. Let's say this is actually a semi lattice rectum. Okay, I'll denote this as L. Okay, now from here let me extend this directrix so that it should hit on through that. Now I am extend this directrix again here. Okay, now this is going to hit here. Okay, now this is going to hit there. So let's say this point is Q here, and now this point is going to be D2 here. I hope this is clear for you. Now we have radius R for this curve. We have some point P, and from P here you are going to hit here to the directrix. So this is going to be the directrix. Okay, you can see this is directrix. Okay, let's say this is going to be the directrix. Okay, or whatever color you use, you should be in a position to remember it off. Okay, you should be in a position to understand yourself. So this is directrix. Okay, now here we need to make some geometrical assumptions. It's not the assumptions, maybe the definitions we can tell. So from here we can tell your radius distance, okay, your focus distance fp is equal to r, is it not? So fp divided by pd1. Okay, now let's say Your FP is actually your R. So R divided by PD1 will give me something called your E value. And if you ask a question why, it's because this is going to be your R, or this is going to be your R, and this is going to be your PD1. So R divided by PD1 gives me, as per the basic definition we have already seen. Okay. I think there is not much confusion. So that means you can tell PD1 is going to be R divided by E. Okay, soon once you get the values, it's a good practice to mark everything here. So PD1, we know this is going to be R divided by E, which is okay. Okay. Now let's say if this is going to be R by E, now probably this is also going to be R by E. Because if you study the parallel theorem, you can see that this is going to be equal one because it's a side of or a rectangle. So it is going to be R by E for PD1. So again, R by E for AB. Now let's say what is going to be FA. Again, from here also you can get some distance. Your FA is going to be, if this is R, this is theta, then your hypotenuse side we have, adjacent side we have. So adjacent side is basically given by R cos theta. So that is going to be your FA. Okay. Your FA distance is going to be R cos theta. Okay. That means your FA is r cos theta, your AB is r cos theta, and what about this QD? So QD is going to be your r cos theta plus r by E. Okay, is it not? So QD2 is also equal to what? R cos theta plus r divided by E. I hope this is clear. But you have one more QD2 here. Why? Because you have a distance from F to Q, that is your semi-lattice vector, which is given by L. Okay, L divided by your QD2, which is given as E as per this concept. Now your QD2 is going to be L divided by E. Again, you mark that here. Okay, this is also equal to so your QD2 is also equal to L divided by E. Okay, your QD2 is also equal to L divided by E. Now you look at the curve. Your QD2 is equal to L by E, but your as per the geometry you have R cos theta plus R by E. So what you do? You equate it. Okay, that means your L divided by E is going to be equal to R cos theta plus R by E. Now you do some simple stuff. Your L is going to be equal to Re cos theta plus R divided by E times E. Your E get cancelled off. Now you end up with L is equal to Re cos theta plus R. Now you take R common. So this R is going to be a common one. So 1 plus E cos theta you can get. Or E cos theta plus 1. It's one and the same. Now you end up with this equation. Your R is going to be equal to, okay, your L divided by 1 plus E cos theta. So this is the basic conic equation which we have already derived just right now. Okay. Now this is the conic equation where R and L represents the basic meaning. So R is equal to L divided by 1 plus cos theta. Because here we have taken QD2, which is going to be equal to exactly same of the combination FA plus AB. So FA is R cos theta plus R by E. So that is where QD2 has written. But as per the definition of QD2 and L, we have written L by QD2 is going to be E. So that means again your QD2 is going to be equal to L by E. So I equate the both two equations. So L by E equal to R cos theta plus R by E. So again that is also going to be give me a good relationship with R and L. So R is equal to L by 1 plus E cos theta. So if cos theta, if E is going to be a 0, then probably it obeys the circle equation. R is equal to L. The radius is going to be equidistant from the center. So like that you can get different equations for different conic profiles. Okay. Now, normally in every textbook, they're going to write R is equal to L divided by 1 plus or minus e cos theta. This is also correct. Okay. Because why it happens like your direction of the directrix is in the uh, right side. Okay. So that is the reason you are getting a plus sign here. If it is on the right, if this directrix is on the right left side, then probably you are going to end up with a minus sign. Okay. So in order to generalize this term, so normally we go with L by 1 plus or minus e cos theta. Okay. So both this and this are correct. So in this context, I think we have derived the basic conic equation, and by generalizing is also you can write L by 1 plus or minus e cos theta, which is also another insight which you can get. Okay. I hope this video is clear for you, and if there are any confusion regarding the geometries, please let me know. This is pretty simple. If you want me to explain once again, please let me know. We'll do that again. Okay, but this is again a self-explanatory based upon the geometry. The only confusion you will get here is only QD2, because QD2 we already seen this is L by QD2, which is going to be E. So your QD2 is going to be L by E. But as per the geometry, your QD2 is going to be equal to the combination of R cos theta plus R by E. So that is what I have written. So only thing you have to equate the two equations which I have written on the top. Remaining everything is just a geometrical thing. Ultimately, you just need to equate the last two equations on the top. So, and you end up with this important result. So this is the basic conic equation which we have derived. So hope you all like this video and try to practice by yourself so that it will give you some good insights and you will come to know where you are going to use it. So we'll catch you in the next video then. Thank you so much.